And so I said, okay, Noah, we'll videotape this. So everybody say hi to Noah.
You know.
Hey, Noah. There we go. So he'll hear you there.
He's sick or on vacation?
No. The orchestra is practicing today. Okay? So here we go. I actually am going to skip. Let's pull up your PowerPoint first. This is how we're starting today. Okay? This is where I'm going to start, and I'm actually going to skip the first couple slides. Okay? Because this should be review from yesterday. This should be review. So we're on the front. We're still on the front here. Okay? But this is what we did yesterday when we were doing all this. Okay? When we were doing this, what these slides are just going to, I'm going to go real fast because you already have this summarized here. Okay? Types of mixtures. Heterogeneous. Suspension colloids, some fit into that. Some of your colloids are actually, we pretended yesterday that milk was our colloid, but there are other colloids that are not homogeneous. Okay? Now, homogeneous solutions, colloids. Okay? When we talk, and this is going to be our focus today with the math. Solutions, small particles. This is again all filled out for you, or mostly filled out. Okay? Mostly filled out because this is what we did on the chart yesterday. Solutions, less than a nanometer, they do not settle. Colloids are medium size, 1 to 100 nanometers. And examples, here's a few more. Yesterday we just talked about milk. You might want to jot down jello, paint, underline that, highlight it, because that'll help you. The particles don't settle. You know, paint, for the most, unless you leave it hanging around for a couple of years, it will be uniform throughout. Suspensions, that was our dirt. Okay? Lots of particles, you could actually see them, clay and water, dirt and water. Okay? Tyndall effect, sorry about that, this should be effect. Can light pass through? And if light does not, okay, if light passes through, it does not exhibit the Tyndall effect. And so if light is not able to pass through, that is called the Tyndall effect. Now, who showed that? Our milk, our suspension, our dirt. Okay, you could not see the light through that. That is the, did it go too far? Now, suspensions. Heterogeneous mixtures, again, larger particles. As a matter of fact, they're so large they can settle. And that, again, was our dirt. So I think you need to jot a note or two on this one. Stirred or agitated. Okay, I believe that's what you need. Particles in a snow globe would be an example there. Particles in a snow globe would be an example. Suspensions. I could have separated my dirt with filtered paper. We could have separated that. Okay? Larger particles don't allow light to go through, therefore they do exhibit the Tyndall effect. Colloids, okay, some examples again, jello, egg whites, paint, blood. A colloid has, the particles are dispersed, but they don't settle out. You got a whole lot of different cells in your blood, but they won't settle out. They may appear cloudy. They may appear cloudy in a solution. And that's why they do exhibit, okay, the Tyndall effect. Okay. And they will exhibit the Tyndall effect. Particles are intermediate in size. Intermediate. Small enough to be suspended, can't be separated. Now this is what we're really going to dwell on today. Whoops, a little too energetic there on my clicking. A solution. This is what we're going to try to work with today. A homogeneous mixture of two or more substances in a single phase. We got salt water, motor oil. Homogeneous look the same throughout. Today we're going to talk about some copper 2 sulfate. Okay, we're going to talk about copper 2 sulfate. That's a solution. Salt water, motor oil, copper 2 sulfate, they look the same throughout. The particles are so small, okay, you can't see them, and if I had a flashlight, it would definitely go through, so it does not exhibit the Tyndall effect. Now, types of solutions. We always want to think of solids, dissolved, and aqueous, okay? But there are other kinds. gases, liquids, solids, alloys. Now again, you guys don't work with alloys too much. Well, we use them, but you don't make them because you've got to get very high temperatures to get the zinc to meld with the copper. It's called smelting. Silver and copper, okay? That's what sterling silver actually is. Some of you might have some sterling silverware. And the two or more metals are uniformly together. Right proportion will give you what you want. We all love 24 karat gold, but we really can't afford it, especially now, right? Okay, so we'll settle for 14 karat gold. I got the 24 there, but that was long ago and far away. 14 karat gold is actually a mixture of gold and silver. And actually some of us like that better because real gold sometimes irritates skin. Okay, so that's why some people wear that.
Irritates skin.
Mm-hmm. Yeah, like sometimes, like if I wear sometimes some certain things and you've got your sweat, you're going to get a little reaction going there. That's salt with the metal. All right.
Wear certain things, like I could only wear gold.
Pure gold, the 24 karat. Yeah, see that, and different people are different.
Because it makes my neck and like my hands
Break out. Some people, I sometimes turn black. Okay, just black. Solute is solvent. You know, when you wear your bling, Spencer, is that what happens too? Okay. Solute and solvent is what's in your solution. So we're going to talk about that. We're going to talk about how much solute dissolves, and usually it's always the lesser amount, dissolves in a solvent. You okay there, Michaela? Or just visualizing the free throw line tonight? Like Nate, nice job last night. Way to hit him when he counted. Okay, so Michaela's just sitting there like that.
Good job, Nate.
Okay. Solute is going to be the amount present in the smaller amount. Solvent is going to be present in the greater amount. Now, universal solvent is what?
Water.
Water. Good. Here's some other combos. Gas. You can mix oxygen and nitrogen. You can mix gas and liquids. That's called soda. Liquid and gas, there's water and air. Okay, that's why sometimes when I do bubble demos, the bubbles won't form as well because there's too much water in the air. Liquid, alcohol and water. Alcohol dissolves perfectly in water. Liquid, solid, mercury and silver. This is what we're going to focus on. Solids dissolving in liquids. Sugar and water. Copper 2 sulfate in water. Okay? Potassium permanganate. Solid would be copper and nickel. Now, this is your summary. So fill this chart in, whatever parts you don't have, I think, or actually what you want to do is just underline. This needs to be memorized. This is always all kinds of multiple choice. Okay? So what we want to know here is what's a solution, uniform blend, homogeneous, salt water, colloids, medium-sized particles. They don't separate out. Is it homogeneous? Is it heterogeneous? We said yesterday borderline. Gelatin, fog, milk. And they do exhibit the Tyndall effect. Suspensions also do. And again, examples would be oil and water or dirt and water. Okay. Let's see. I want to get to the, will things dissolve? Okay. If they do, we say they're soluble. If they don't, we say they're insoluble. Obviously, my copper 2 sulfate was soluble. It dissolved in the water. Again, this was that blue compound that we started with. Insoluble means it won't. Like oil won't dissolve in water. So we call it insoluble. Okay? Like dissolves like is what chemists call this. And what we're going to do is we're going to talk about polar ends of molecules. A polar means slightly positive or negative. Nonpolar, no charge. No charge. Okay? You are most familiar with this. When you have a polar solvent, which is our water here, and I'll show you why in a second. Nonpolar is when you have nonpolar solvents will dissolve nonpolar solutes. Now, examples of that, you don't use it much. Dry cleaners. Okay? Dry cleaners. When you can't get dirt out, when you throw your clothes in the wash, okay? Or you have this kind of material that shouldn't go in the wash because we know that water won't clean it. You take it to the dry cleaners. Now the dry cleaners use a nonpolar solvent. They usually use carbon tetrachloride is what they use. Okay? And that's why they smell. Dry cleaners, you go in, it smells. Okay, but that's usually what they're using as a nonpolar solvent to get your nonpolar dirt out. That's what they're doing with that. Okay, so we're going to talk about this other one though most of the time, just so you know that that exists out there. Oil and water don't mix. Now, what makes water polar? And again, that's why I brought out Mickey today. Okay, Mickey. Now, when we did, okay, no, it's Mickey. Okay, hi Bronte, you too. Oxygen, electron dot structure. Okay, remember those, like this, I don't like this diagram because it doesn't have some lone pairs. Okay, and what we have with water is we've got some lone pairs. Lone pairs of what? What are these over here? Electrons, and what are they charging? Negative. Now, it's not a whole negative. Okay, if I have sodium and chloride, positive, negative, I'm going to use this funky little delta sign. Delta, that's what this is. And so oxygen, because it has those lone pairs in water, is going to be slightly positive, and the hydrogens are going to be slightly positive. Water, did I say it wrong? Okay. Again, put that delta in front of those. Why the delta? Delta partially negative. Hydrogens then, because it's given all the electrons to oxygen, look at the electrons are much closer to the oxygen, are said to be slightly positive. Because of that, I can dissolve stuff in water. I can dissolve ionic things in water. Okay? So, how does that work? It's called solvation. No, not salvation, solvation. Okay? It's also called, I use the word dissolution. It's also called hydration. Just so you see that you can use any of these terms. Okay? And what it is that our sodium ion, let's throw some salt and water. It will dissolve. Why? Because Mickey's head is slightly negative. So all opposites attract, okay, and that's in relationships too, don't get married though. We have slightly negative is going to be attracted to the positive, okay? Now guess what happens with the chloride? So positively charged ions are attracted to the negative ones. Here's my negative chloride. Look at Mickey's ears. They're slightly positive, so they're attracted to the negative. And I usually ask you to kind of draw this, okay? Usually ask you to draw or describe solvation or hydration. So let's show you a couple little videos here. Let's see, where'd that end up? This one? Yeah. Okay?
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water.
It's not really blue. Okay.
Click on the zoom button to view sodium chloride dissolving in water.
Okay.
Polar water molecules
Look at Mickey's
interact with
ears.
the positive and negative ions of a salt.
Going to get
Positive
the
ends of the water
negatives.
molecules are attracted to the negative chloride ion. The negative ends of the water molecules are attracted to the positive sodium ion.
Okay. Just
This
keeps chipping
interaction
away.
between water and the salt ions causes a salt to break apart or dissolve in water.
And again, notice how Mickey, with the negative, the ears are going. The positive ions are being attracted to Mickey's face. I got another one here for you. Let's see, KMNO4.
When ionic compounds dissolve, their ions separate from the crystal lattice of the solid and are surrounded by water molecules. The dissolved ions are said to be hydrated in solution. No longer in contact with each other, the ions can now react with other substances in solution.
Okay, so there we go. That's solvation, dissolution, hydration. Okay, they're all the same thing. And that's what we're going to do now is let's throw some salts in water, okay, and do some calculations. So back to the first page, okay, back to our first page. How much salt is in your water? Whoops, I was writing a lot, wasn't I? Okay, okay. So back to the first page of the PowerPoint. And then I thought it was important that we understand first the nature of our solutions, and then we can do our calculations. Okay? So here we go. We're back to the front. I'm actually going to stop because I know when I upload